All right, today we're going to learn about similar figures and scale drawings. Now, I'm showing you a page in the book because I want you to show you a little bit in a picture of what we're doing. If you can see here, we have two triangles, and those two triangles are similar to each other. Now, similar figures have the same shape, but not the same size. So let's fill that in our definition sheet here. Similar figures have the same shape, but not necessarily the same shape, but not necessarily the same size. If you need a pencil, Ms. Rapp, she's sharpening one for you. All right. Necessarily the same size. The same shape, but not necessarily the same size. A-R-I-L-Y. All right, now, when we look at these similar figures, Ms. Robinson, Kylie needs a sharpened pencil.
I'm not sure what's up with all the side conversations, but you need to stop. And Mrs. Kuzman, maybe if you can start writing names on your piece.
I have about 7 already, so. Okay. Guys, we're going to continue, and I need you to pay attention, please. When we're talking about similar figures, we have triangles here. And what is similar about them, and it's very important because when we talk about similar triangles, there's certain parts of the triangle that are similar to the other part of the triangle. So notice how angle A is 64 degrees and angle X is 64 degrees. Angle C is 55 and angle Z is 55. Angle B is 61 and angle Y is 61. So they have similar properties. Now, similar figures, back to our note sheets, similar figures have corresponding angles that have equal measure. And then the lengths of their sides, folks, are proportional. So they're equal and proportional. Angles have to be equal, the sides are proportional. And that's what...
Is it P-O-R?
Pro and then P-O-R. Yep. Pro-por. Now, and this kind of connects it to our lesson from Monday in that we learned about proportions, but now we're going to relate them to figures. And it makes it a little bit more fun. It puts a little more meaning behind why did we learn about the proportions. All right, if we look at, we're going to come back to these two here in a few minutes. This symbol, this little squiggle line, you know how we talked about mathematicians always want to find little shortcuts to make things shorter? This symbol right here means is similar, to. So that little symbol means is similar to. Now it's important, like I mentioned a few minutes ago, that when we look at triangles, we say the similar parts in the same order. So right here, the symbol, the squiggle sign, means is similar to. And then at the right, notice how it says triangle ABC. So it starts at the top, goes to the right, and then down. And that's similar to triangle XYZ. Now you can't say ZXY or YZX because the first letter here, A, is the same angle as X. So that's why it's important that they're both listed first. And so the order is really important here. All right, so let's remember that as we do our examples today. All right, so let's look at this trapezoid. So it says trapezoid ABCD is similar to trapezoid EFGH. So A corresponds to what? E, good. And B to F, C to G, D to H. Nice job. So this is where we get to set up our proportions. We have a big trapezoid and we have a small trapezoid. We have trapezoid 1, we have trapezoid 2. It doesn't matter what you call them, you just have to call them something. All right? So let's call this the big trapezoid and the small trapezoid. So when we set up our proportions, we know which one to put on top and which one to put on the bottom. Now, it looks to me, in this example, they put the 6 on top. So what they did the big trapezoid over the small trapezoid. Now, side AB, which is right here, corresponds to what side? EF, thank you. And don't forget to write your little bar on top saying that it's a line segment.
You know what, you just ran your pencil across AB, why don't you run it across EF so that
Oh,
you
yep.
can see what
AB, EF. So those are corresponding sides in the trapezoid.
So if you put it in your, put the big one in your shrinking machine, it would
Yeah.
match up that side.
Yep. And that's kind of a cool thing to think of it as a machine. You know, your machine is going to have a factor, or your machine is going to have a sizing of something either greater or smaller. So here we're going from the big to the small. So we set, okay, this side here is 6. What side is it in the small trapezoid? Yep, and they call it length K. And then side CD, which is down here, corresponds to HG, and this is 2. So we have 6 over K equals 3 over 2.
You know, when I first glanced at that, my brain had a problem with it because that's not the only way you can set it up. My brain wanted to put 6 over 3,
Uh-huh.
K over 2, how it looks in the picture, and that's okay too, you'll get the same answer.
Now, and what Ms. Robinson was saying is that you could set, because what are we comparing? We're comparing big to small, or we're comparing like the top line to the bottom line, right? So you could set it up top to bottom if you wanted to. So you can set up proportions as long as you know how you're setting them up. You can set them up 3 or 4 different ways depending on, you know, what you want to do with them. And that was a good point. All right, so 6, doing our cross products here, 6 times 2 is K times 3. And what is 6 times 2? 12. So I'm just going to write a 12 here. And what are we going to divide each side by now to get K by itself? 3. So 12 divided by 3 is 4. Now what's nice about these examples is some of you might have known that in your head already, because if we look at proportions here, what is 6 to 3? Isn't that doubled? Double 3 to get to 6, right? So we would have to double 2 to get to 4, and that's what we got. So, you know, sometimes you know the answer in your head before you do the process because it's a nice scale factor. Like this is just doubling it or cutting it in half depending on which way you're looking at it. Cutting it into 2/3 depending on which way you're looking at it. All right, let's flip it over here. Now, well actually let's fill in a definition. Indirect measurement, and this is the one that is kind of fun and a lot of people use these, especially in like land surveyors or when building certain things. When an indirect measurement is using similar figures to compute distances. So using similar figures to compute distances that are difficult to measure directly. Using similar figures to compute distances that are difficult to measure directly. And you'll see what I mean by that in just a minute. If you physically can't measure a distance, then we use the indirect measurement. All right, give me a thumbs up when you got it down so I know when we're good. Using similar figures to compute distances that are difficult to measure directly. Good, still waiting on a couple thumbs up. All right, and this is one of my favorite examples of this. A flagpole. Now, believe it or not, I've actually used this, kind of being the nerdy math teacher that I can be sometimes when we're at the playground with Calvin and Callie. Calvin will say to me, "Mom, how tall is that slide?" And I'll say, "I don't know." But then in my head I'm thinking, "Oh, I bet I can figure that out." Because of this, instead of the flag, I think of it as a slide. And if the sun is out, then it's really easy because shadows can be your friend. In this instance specifically. So, when we are at the playground, sometimes I'll actually have Kelvin help me figure out the shadow. I know that's kind of dorky, and I'm sure he'd rather just be sliding down the slide, but you can never start too early, right? Even though he's only 3. Okay, so we know a flagpole casts a shadow 5 feet long. At the same time, a yardstick casts a shadow 1.5 feet long. The triangle shown for the flagpole and the shadow is similar to the triangle shown for the yardstick and its shadow. So our goal here is we want to figure out how tall is that flagpole. Without actually climbing up and, dropping a tape measure down or something, this is using that indirect measurement. We can't really physically jump to the top of the flagpole to see how tall it is, so we're going to use this to help us. So we know that corresponding sides of similar triangles are in proportion. Proportion. All right, now this one, again, they set it up, and you can set it up differently, but it looks like they put the yardstick on top and the flagpole on the bottom. So we'll just write that down so we can remember. Yardstick on top, flagpole on the bottom. Another way to set it up, if you wanted to, you could do length of shadow to height. Length of shadow to height. That's another option that you could do. Okay. All right, so let's take a look here. We have the ground shadow is 1.5 in the yardstick. What's the ground shadow for the flagpole? What's the ground shadow for the flagpole? 5. Okay. Now, the yardstick is 3 feet, right? And we don't know how many feet tall the flagpole is, so that's where our variable is going to go. Now, this is what we've done the last few days. Using our cross products, 1.5 times x has to equal 5 times 3. And now what is 5 times 3? Okay, so I'm going to write that in there, 15. What am I going to divide each side by? 1.5. So x equals, what is 15 divided by 1.5, Maria? 10. Nice job. So our flagpole is 10 feet tall. Now some of you might have said you knew that already. Because, what do you know the proportion of 3 to 1/2 is? 1 and 1/2. Half of it, right? So whatever number was going to be here, half of it was going to be 5. So you might have been able to do that. And that's what's kind of nice about these examples is we know what the answer should be before we do it. So we know we're doing the process right.
Well, you know what I like about these problems, and this isn't actually a bad reason I like them, but I know that there have been problems like these on the meat test.
Yes.
You might say, but Ms. Robinson, we'll never have to take a meat test again in our lives, which is true. I don't know if you thought of that yet, but they're the kind of problems, but you'll see it in much more complicated detail. Unlike the SAT and the ACT, you will see problems like this.
Mm-hmm.
So it's definitely a testing kind of thing.
Yeah. All right. Scale drawings. Now this is what I really liked. Now, for those of you who know, or maybe you don't know, Kelvin, he is really into Matchbox Cars. And not any old Matchbox Cars. He is really into Cars. The movie Cars, Matchbox Cars. So, what I found, and we were doing this the other day, is he asked me, Mom, is this the same thing as a big car? And I said, yeah, it is. But I was curious, being kind of their nerdy math teacher I can sometimes be, I wanted to know exactly what it was and what the distance and what the scale factor was. So, because if you think about it, if a car is about, I don't know, 21 to 22 feet, I think, in length is the average car, you'd have to shrink everything down of that car to make it look proportional in a Matchbox car. Do you remember, did any of you have Matchbox cars when you were little? They're pretty detailed, aren't they, for being that small? So you have to take every part and shrink it the same factor so that the car still looks proportional when it's little. We're going to be doing an activity on Friday and next week that has to deal with that. But just to get started, let's take a look at this a little bit more in depth of what it actually means. Another place, can anybody else think of examples of where they use a scale factor to different items? John?
I was going to say those giant things you see.
Yeah, what do you mean by that, John?
It's like a... What are those things called?
Like a tower? Cylinder? A windmill?
It's like 50 feet tall. No. There's one out here.
Like a wind turbine?
Wind turbine.
There we go, yes. Okay, wind turbines, they probably make a replica of it smaller, right? Ms. Robinson was touching on when you do house plans, do you think the architect actually draws out a piece of paper that's going to be the actual size of your house? No, they shrink it down, don't they? Okay? Another one is maps. When you have a map, which is a pretty simple one, right? They always have, 1 inch or 1 centimeter is equal to 10 miles, or depending on how zoomed in you have, right? Those are all scale factors. And so we're going to talk about scale drawings here with a map. Now, a map is 1 inch to 24 miles. So every 1 inch on the map is equal to 24 miles. So on the map, if we have 2 cities that are 3 inches apart, we want to know how many miles in actuality that is. So let's set up a proportion. Map to actual. Okay, so on the map we have 1 inch to how many miles in actual did we say? 24. And if we have 3 inches on the map, we'll set it to D. That's what we're trying to find, the distance. Using our cross products, 1 times D equals 24 times 3. So 24 times 3 is? 72. Thank you, John.
And guys, we don't have to divide this one because we already have 1D. It's
Yep.
all alone, so
Does anybody remember what this might be called? A unit conversion from a few times back. Remember when we have a numerator of, or denominator of 1? Okay, so it's about 72 miles between the two cities. All right, let's try some examples here. Trapezoid, KLMN, is similar to trapezoid ABCD. So let's take our trapezoid here. I'm going to just redraw it from the front page so we don't have to keep flipping. A, B, C, D. And what measurements were on there, guys? 6 and 3. All right, so we want to find the value of y. Let's call this trapezoid 1, trapezoid 2. So does it matter which one we put on top? No, it sure doesn't. So let's do 1 over 2. Trapezoid 1 over trapezoid 2. All right, so trapezoid 1, AB is 6. Trapezoid 2, that is proportional to y. DC is 3, which is proportional to 5. All right, let's do our cross products here. 6 times 5 has to equal 3 times y. What is 6 times 5? 30. What do I divide by to get y by itself? 3. Y equals, what's 30 divided by 3? 10. Are you understanding how to set them up okay? Patrick says yes. What do you else do? Does anybody else say yes? No? What do you think?
Yes.
Now, these folks, I'm going to tell you, it's easiest when you draw a picture. So, we have a building. Let's draw a little building here. Put some windows in it, maybe. Okay, this building casts a shadow.
I can't draw that, so you don't have to draw it.
We'll draw a little stick figure at least so you know, because these I do want you to draw pictures for. So, the building is 70 feet tall, and the shadow is 150 feet. All right, then we have a nearby flagpole. And this shadow of the flagpole is what? 60 feet. So we have 70 and 150 and 60 and F, the height of our flagpole.
Is the 70 over on the side?
Yep, 70. My pencil's kind of not showing up very well. It's kind of shiny. I don't know if that really helps or not, but okay. All right. 60. 150, because remember, here's our numbers. 150, 70, and 60. All right, now, we can set these proportions up two different ways. We can say shadow to shadow, height to height, or we can say building to flagpole. What do you want to do? Shadow to shadow? Okay. So if we do that, so you're saying shadow to height, John. Okay, so we'll do shadow over height. You can just draw a little triangle if you want, Tamara. Okay, so we want the shadow on top. So let's do the big building first. So the shadow is what of the big building? 150. And the height of the building is 70. Shadow here is 60. And then over F, which is the height of our flagpole, which we don't know. All right, let's use cross products. 150 times X, or F, excuse me. 150 times F equals 70 times 60. 7 times 6 is 42 with our 2 zeros. 150F. What am I going to divide by? 150, good, thank you. So 4,200 divided by 150, 28. Now what does 28 mean? What is 28?
7 times 8, 4.
Look at the
7 times 4. 7 times 4.
But what is the flagpole height? Thank you, Vanessa. I know, they always do that. Yeah, I think maybe because most people obviously see flagpoles and trees. All right, last example here for a map. The distance from Atlanta to Macon is about 75 miles. On a map whose scale is the same as it was in example 3. So let's look at example 3. We have map over actual. And we're using the same scale. The same scale was 1 to 24. So
Map over what?
actual, your actual distance. No, I don't. All right. Now this time, though, what's our distance? 75 miles. Is that in inches on the map, or is that in actual? Actual. So we're going to put that on the top or bottom? Bottom. And we want to figure out x on top, which is the distance between the two cities on the map. So 1 times 75 equals 24x. Divide by 24. X equals, because 24 times x, 1 times 75. X equals 3.125 inches. Yep. Are there any questions about these 3 examples so far? We're going to do the practice sheet here in a second, so we'll do some more examples. All right.